Hello there and welcome to Zero Drift, your peaceful passage through the universe. Tonight, we are going to explore one of the most beautiful and mysterious equations in the history of human thought. An equation that does not describe the motion of planets, or the flow of electricity, or the behavior of heat. It describes something stranger and more fundamental than any of those things. It describes the behavior of reality itself at its smallest scales, the way that particles move, the way that energy organizes itself, the way that the universe decides in a manner that is irreducibly probabilistic and irreducibly strange, where things are and what they are doing. This is the story of the Schrödinger Equation. It is the story of a young Austrian physicist who spent years wondering whether he would ever make a contribution worthy of the giants who had come before him, and who then, in the space of a few remarkable months, produced an equation that would change physics forever. It is the story of matter waves and wave functions and probability clouds, and the deeply unsettling discovery that the universe, at its most fundamental level, does not deal in certainties but in possibilities. And it is, woven through all of that, a human story of curiosity and doubt, and the particular courage it takes to follow a mathematical idea into territory that no one has ever visited before. So settle in. Let your body grow heavy and still. Let your breathing find its own slow rhythm. And allow the story of the Schrödinger equation and the quantum world it opened to carry you gently towards sleep. Vienna, in the late 19th century, was one of the great intellectual capitals of the world. It was a city of coffee houses and concert halls, of philosophers and physicians and painters, of Sigmund Freud constructing his theories of the unconscious mind, and Gustav Klimt painting his gold-leaf visions of beauty and desire. It was a city that took ideas seriously, that regarded the life of the mind as one of the highest callings available to a human being, and that produced, in the decades around the turn of the 20th century, a concentration of genius that has rarely been matched in the history of civilization. It was into this city, on the 12th of August, 1887, that Erwin Rudolf Joseph Alexander Schrödinger was born. His father was a botanist and amateur painter with wide intellectual interests, and his mother came from a family of distinguished scientists. The household into which Schrödinger arrived was one where learning was natural and curiosity was encouraged, where books lined the walls and conversation ranged freely across subjects that a narrower household might have kept carefully separated. It was, in short, an excellent place to be born if you were going to become one of the most important physicists of the 20th century. As was customary among families of their class and intellectual ambition, Schrödinger was educated at home for the first 11 years of his life, receiving a broad and careful education from his father and from a series of tutors before he was old enough to attend the local gymnasium school. He arrived at the gymnasium already unusual, a boy who had absorbed not just the sciences but languages and literature with equal ease, who could move between subjects with a fluency that suggested his mind was not organized in the compartmentalized way that school curricula tend to assume, but rather as a single connected whole, where everything illuminated everything else. From almost the first day he arrived at the gymnasium, Schrödinger excelled. Mathematics and physics were his strongest subjects, as they would remain throughout his life, but he was not merely technically proficient in the way that many gifted students of those subjects are. He had an aesthetic sense that accompanied his analytical ability, a feeling for the elegance of an argument, a preference for approaches that revealed the structure of a problem rather than merely solving it, a sensibility that would eventually express itself in the particular quality of his most important work. He left the gymnasium 8 years later at the top of his class and arrived at the University of Vienna expected to do great things. He did not disappoint. His years at Vienna were marked by the same combination of breadth and depth that had characterized his earlier education. He studied physics with rigor and passion, but he also read widely in philosophy and literature, attended concerts, learned languages, and developed the intellectual personality that would remain his throughout his life. Serious but not narrow, rigorous but not dry, deeply committed to physics, but always aware that physics existed within a larger human context of meaning and beauty. In 1910, Schrödinger received his doctorate from the University of Vienna. He was 22 years old. The world seemed to be arranged for his convenience. But then, as it has a tendency to do, history intervened. Let your breathing slow now. Let the world outside grow quiet and soft. The story moves forward through the early years of a life that will eventually produce one of the great equations of physics, but it does so through disruption and uncertainty and the long patience that all genuinely important work requires. The First World War came in 1914 and took Schrödinger, like so many of his generation, away from the work he had been building toward and sent him instead to the front as an artillery officer. He served competently, survived intact, and returned to academic life when the war ended, carrying with him, as all survivors of that catastrophe carried, a knowledge of what the world could do to carefully laid plans and quietly nurtured ambitions. After the war, Schrödinger moved between institutions, spending time in Vienna, in Stuttgart, in Breslau, seeking a permanent position that would give him the stability and the time to do the work he felt was in him. The years passed with a restlessness that was partly circumstantial. The academic job market in post-war Germany and Austria was difficult and partly temperamental. Schrödinger was drawn to ideas from many directions and found it difficult to commit himself exclusively to any single line of research. He worked on problems in thermodynamics, in the theory of color perception, in general relativity, in the biology of inheritance. He was never idle, never without interesting things to think about, but he had not yet found the problem that would call forth his deepest abilities. Finally, in the early 1920s, he arrived in Zurich, Switzerland, where he settled into a position at the university at the age of 34. Zurich was a good place to be a physicist in those years. It was a city of relative calm in a continent still recovering from the devastation of the war, and the physics department there was active and engaged with the most important questions of the day. As the next few years passed, however, Schrödinger began to wonder privately whether his best years might already be behind him. He was approaching 40, an age that physicists of that era sometimes spoke of as a kind of deadline, a point past which the revolutionary contributions tended not to come. It was a belief not entirely without foundation. The history of physics did suggest that the great theoretical breakthroughs tended to come from young minds that had not yet accumulated the weight of received wisdom, minds that could see familiar things as if for the first time and ask questions that more experienced physicists had stopped asking because they seemed too basic or too strange. Schrödinger was by 1925 a very accomplished physicist, widely respected, published in many areas, clearly gifted. But he had not yet made the contribution that would place him in the first rank of his contemporaries. He was aware of this, and it weighed on him. Then, in October of 1925, he read a paper. The paper was by Albert Einstein, and it concerned some of the latest developments in atomic physics. Einstein was already, by this point, one of the most celebrated scientists in the world. His special and general theories of relativity had made him internationally famous, the kind of scientist whose work was reported in newspapers and discussed by people who had no particular training in physics. But it was not the main argument of Einstein's paper that caught Schrödinger's attention. It was a footnote. The footnote mentioned the recent doctoral thesis of a young French physicist named Louis de Broglie, who had proposed something startling about the nature of matter. De Broglie had taken seriously a question that most physicists had not yet found a way to ask systematically. If light, which everyone agreed was a wave, which Maxwell's electromagnetism described as oscillating electromagnetic fields propagating through space, could also behave like a particle, as Einstein himself had shown in his explanation of the photoelectric effect, where light knocked electrons from metal surfaces in a way that only made sense if light came in discrete packets of energy. If light could be both wave and particle, then could matter be both particle and wave? This was the question de Broglie had asked in his doctoral thesis, and his answer was an unequivocal yes. He proposed that for any material particle, any electron, any proton, any atom moving with a momentum p, there was an associated wave with a wavelength given by Planck's constant divided by the momentum. The faster the particle, the shorter the wavelength. The heavier the particle, the shorter the wavelength. And associated with the energy of the particle was a frequency given by the energy divided by Planck's constant. These were extraordinary proposals. They connected the particle properties of matter, momentum, and energy, the quantities that appear in Newton's equations of motion, with the wave properties of frequency and wavelength, in direct analogy with what Einstein had shown for light. De Broglie was saying that matter, like light, had a dual nature. That the electron, which everyone knew was a particle, it had a definite mass, a definite electric charge, it left tracks in cloud chambers, it could be deflected by electric and magnetic fields, was also, in some deep and not yet fully understood sense, a wave. The experimental evidence for this proposal was, at the time de Broglie wrote his thesis, essentially non-existent. He was working from theoretical considerations, from analogies, from a conviction that the wave-particle duality that Einstein had revealed for light must extend to matter as well. The physics community received his ideas with cautious interest, but not with widespread excitement. Without experimental confirmation, it was difficult to know how seriously to take them. But Einstein had taken them seriously enough to mention them in a footnote, and that footnote caught the eye of Erwin Schrödinger in Zurich. Drift a little deeper now, let the night grow quieter still. The idea that matter might be a wave, that the electron, that apparently definite and localized particle, might also be something spread out in space, something with a wavelength and a frequency, something that could interfere with itself the way water waves interfere when they overlap. This idea was about to transform physics, and it was Schrödinger who would take it and make it into a theory. Schrödinger read de Broglie's thesis with immediate excitement and wrote to Einstein to share his enthusiasm. A few weeks later, he was asked by the physicist Peter Debye to give a talk on de Broglie's ideas at a physics colloquium in Zurich, a regular gathering where physicists presented and discussed the latest developments in the field. Schrödinger gave what was, by all accounts, a beautifully clear presentation of de Broglie's wave-particle duality. He explained the essential idea that matter particles had associated waves, that the wavelength was inversely proportional to the momentum, that the frequency was proportional to the energy, with the clarity and elegance that characterized his best pedagogical work. But when he finished, Peter Debye raised an objection. It was not an objection to the physics, exactly, but to the form of the theory. Debye pointed out something that seems, in retrospect, almost obvious, but that de Broglie had apparently not considered and that no one else had yet raised in quite this way. If particles behave like waves, Debye said, then there should be a wave equation. Every other kind of wave in physics, sound waves, water waves, electromagnetic waves, waves on a vibrating string, was described by a wave equation, a differential equation that governed the behavior of the wave, and told you how it would evolve in space and time given the conditions it was subject to. De Broglie had proposed that matter particles had associated waves, but he had not provided a wave equation for those waves. How could you have waves without a wave equation? Schrödinger heard this objection and felt the force of it immediately. Debye was right. You could not simply say that electrons were waves and leave it at that. A wave is defined by its wave equation. The wave equation tells you how the wave behaves, how it responds to obstacles and boundaries and forces, how it propagates and interferes and changes over time. Without a wave equation, de Broglie's proposal was more of a metaphor than a theory. And Schrödinger, almost at once, decided that he would find the missing equation. What followed was one of the most productive periods in the history of physics. Schrödinger retired from the social obligations of the holiday season at the end of 1925 to a villa in the Swiss Alps with a notebook, a pencil, and the problem. He worked intensely with the focused energy of someone who has finally found the problem he was born to solve. And in the space of a few months, by the beginning of 1926, he had it, the Schrödinger Equation. To understand how he arrived at it and what it means, we need to think carefully about waves. Not quantum mechanical waves initially, but ordinary classical waves, the kind you see when you drop a stone in a pond, or watch the ocean, or listen to the sound of music. A simple wave moving in one direction through space can be described mathematically by a function that gives the displacement of the wave at every point in space and at every moment in time. For a pure, simple wave, a wave of a single frequency and a single wavelength, moving steadily without changing its shape, this function takes the form of a cosine or a sine, oscillating in both space and time with a fixed relationship between its spatial scale, the wavelength, and its temporal scale, the period. This wave function satisfies a wave equation, a specific differential equation that relates the way the displacement changes with respect to space to the way it changes with respect to time. The wave equation has a very particular structure. It relates the second derivative of the displacement with respect to position to the second derivative with respect to time, with a factor of the wave speed connecting them. And this structure ensures that sinusoidal waves of fixed frequency and wavelength are solutions, and that the relationship between frequency and wavelength is the correct one for the physical situation being described. This was the framework Schrödinger was working within. If matter particles were associated with waves, and if those waves obeyed a wave equation, then the structure of that wave equation would determine everything about how the matter waves behaved, how they propagated, how they responded to forces, what shapes they took when confined in different ways. Finding the wave equation was not merely a technical task. It was the task of formulating quantum mechanics itself. Schrödinger approached the problem with a set of requirements that any acceptable wave equation would have to satisfy. First, it had to be consistent with de Broglie's relations. The wavelength of the wave had to be connected to the momentum of the particle in the way de Broglie had proposed, and the frequency had to be connected to the energy. Second, it had to be consistent with the basic energy equation of classical mechanics. The total energy of a particle is the sum of its kinetic energy and its potential energy. Third, it had to be linear. If two different wave functions were both solutions, then any combination of them should also be a solution, because this linearity was what allowed waves to interfere and superpose. And fourth, when there was no force acting on the particle, when the potential energy was constant, the equation should have sinusoidal traveling wave solutions, because in that case, the particle moved freely with constant momentum and energy. These requirements, taken together, severely constrain the form the wave equation could take. And working through the mathematics with care and with a willingness to follow the algebra wherever it led, even when it led somewhere unexpected, Schrödinger arrived at his equation. Let your mind rest gently on that image, a physicist in a mountain villa in winter, working through page after page of mathematics, following the logic of waves and energy and the strange proposals of a young French physicist, pressing deeper and deeper into the structure of the problem until the equation finally emerged, complete and beautiful, from the fog of calculation. One of the first things that emerged from the mathematics was something that might, at first glance, seem like a problem. The wave equation that satisfied all of Schrödinger's requirements was not a wave equation in the classical sense. Classical wave equations related the second derivative of the wave with respect to space to the second derivative with respect to time. But the equation Schrödinger arrived at related the second derivative with respect to space to the first derivative with respect to time. And more than that, it contained the imaginary number the square root of -1, a mathematical object that appears in no classical wave equation. This emergence of the imaginary unit was not a sign that something had gone wrong. It was, in fact, a sign that something important was happening. The mathematics was insisting that the wave function of quantum mechanics, the function that Schrödinger's equation described, was not a real-valued function, but a complex-valued one. It had both a real part and an imaginary part, both of which were needed to fully specify the quantum state of the system. Complex numbers are familiar to mathematicians and engineers, though they can seem mysterious to anyone encountering them for the first time. A complex number has the form a plus I times b, wherein b are ordinary real numbers and I is the imaginary unit with the property that its square is -1. You can think of complex numbers as points in a two-dimensional plane, where one axis represents the real component and the other represents the imaginary component. And complex exponentials, exponential functions with imaginary exponents, trace out circles in this complex plane, oscillating between real and imaginary components in a way that is deeply connected to the behavior of ordinary sines and cosines. The fact that quantum mechanical wave functions are complex is not a weakness of the theory. It is one of its most characteristic features, and it has deep physical significance. A complex wave function cannot be directly measured. No physical instrument can return a complex number as its reading, only a real one. This means that the wave function itself is not directly observable. It is not like the displacement of a water wave, which you can see and feel. It is a more abstract mathematical object, one that encodes information about the quantum state of the particle in a form that requires additional interpretation before it can be compared with experiment. That additional interpretation was provided not by Schrödinger himself, but by the German physicist Max, born in 1926, in one of the most important conceptual contributions to quantum mechanics, important not for its mathematical content, which was relatively straightforward, but for what it said about the nature of physical reality. Born proposed that the physical significance of the wave function lay not in the wave function itself, but in the square of its magnitude, what mathematicians call the modulus squared. For a complex number, the modulus squared is calculated by multiplying the number by its complex conjugate, the same number with the imaginary part negated. The result is always a real, non-negative number. And Born proposed that this real, non-negative number represented the probability density for finding the particle at a particular location. In other words, if you wanted to know the probability of finding a particle in some small region of space, you would take the wave function at that location, calculate its modulus squared, and multiply by the size of the region. The result would give you the probability, a number between 0 and 1, that a measurement would find the particle there. This was a radical proposal, and it changed the character of quantum mechanics in a fundamental way. It meant that quantum mechanics was not, and could not be, a theory that predicted with certainty where a particle would be or what it would be doing at any given moment. It was instead a theory that predicted probabilities, the probabilities of the various possible outcomes of measurements. You could know everything that quantum mechanics had to say about a particle, you could know its complete wave function, and still be unable to predict with certainty the result of measuring its position. The best you could do was calculate the probability of each possible result. This indeterminacy was deeply disturbing to many physicists, and it remains philosophically troubling more than a century later. Einstein, in particular, was never reconciled to it. He believed that quantum mechanics, however accurate its predictions, was incomplete, that there must be a deeper level of description at which the universe was deterministic, at which God did not, as he famously said, play dice with the cosmos. The debate between Einstein and Bohr about the interpretation of quantum mechanics was one of the great intellectual exchanges of the 20th century, conducted over decades in papers and letters and personal conversations, and it was never fully resolved. But whatever one believes about the philosophical implications of Born's interpretation, its practical consequences are clear and confirmed by an enormous body of experimental evidence. Quantum mechanics, with Born's probabilistic interpretation of the wave function, makes predictions that are accurate to more decimal places than almost any other theory in the history of science. The theory works. Its predictions are correct, and the price of those correct predictions is the acceptance of an irreducible randomness at the heart of nature. As you rest in the quiet of this night, let that thought settle gently. Not as a source of anxiety, but as a fact about the universe, a fact as beautiful in its way as any other, the fact that at its most fundamental level, reality is not a clockwork mechanism proceeding inevitably from one determined state to the next, but something more like a sea of possibilities, collapsing into actuality at each moment of measurement, governed by probabilities that can be calculated precisely even though the outcomes themselves cannot be predicted. Let us follow the mathematics a little further into the quantum world, not with the intensity of a student preparing for an examination, but with the easy curiosity of someone drifting through a landscape of ideas, pausing where something is beautiful, moving on when the moment feels right. One of the most important techniques for working with the Schrödinger equation is called separation of variables. It is a mathematical method for simplifying partial differential equations, equations that involve derivatives with respect to more than one independent variable, by looking for solutions that can be written as products of simpler functions, each depending on only one variable. For the Schrödinger equation, which involves both position and time as independent variables, the separation of variables approach looks for wave functions that can be written as a product of a spatial function multiplied by a temporal function. The spatial function depends only on position, the temporal function only on time, and together they describe the complete quantum state of the particle. When this approach is applied to the Schrödinger equation, it splits into two separate equations, one governing the spatial part of the wave function, one governing the temporal part. The temporal equation is straightforward to solve, and its solution turns out to be a complex exponential function of time. The frequency of this exponential oscillation is determined by the energy of the particle. Higher energy corresponds to faster oscillation, in precisely the way that de Broglie had proposed. The energy and the temporal frequency are connected by Planck's constant. The spatial equation, which is known as the time-independent Schrödinger equation, is more interesting and more varied in its solutions. This is the equation that depends on the potential energy of the system, on the forces acting on the particle, and it is this equation that determines the allowed energy levels of quantum systems and the spatial shapes of the wave functions associated with those energy levels. The solutions of the time-independent Schrödinger equation are called eigenfunctions, from the German word for characteristic function. Each eigenfunction corresponds to a particular allowed energy level, an eigenvalue, and together the eigenfunctions form a complete set from which any quantum state can be built by superposition. This structure, a set of allowed energy levels, each with an associated characteristic spatial wave function, is one of the most important features of quantum mechanics. It is what gives atoms their distinctive spectral lines. It is what gives molecules their characteristic vibrational frequencies. It is what determines the electronic structure of solids and the behavior of semiconductors. The eigenvalue structure of the Schrödinger equation is, in a very deep sense, the structure of the physical world at the atomic scale. To make these ideas concrete, let us think about one of the simplest quantum mechanical systems, simple enough to solve completely with elementary mathematics, but rich enough to illustrate all the key features of quantum mechanics. This system is called the infinite square well, or the particle in a box, and it is one of the most celebrated examples in all of quantum physics. Imagine a particle confined to a one-dimensional region of space, a box, in effect, with impenetrable walls at either end. Inside the box, the particle moves freely, subject to no force. Outside the box, it cannot exist. The walls are infinitely high. The confinement is perfect. This is an idealized situation, not something that exists in literal reality, but it captures the essential physics of any situation in which a particle is confined to a finite region. The time-independent Schrödinger equation inside the box, where the potential energy is zero, takes a particularly simple form. It is a second-order differential equation whose solutions are sinusoidal functions, sines and cosines, of the position coordinate. The boundary conditions of the problem, the requirement that the wave function be zero at the walls of the box, because the particle cannot exist outside, restrict which sinusoidal solutions are acceptable. Only those sine functions fit inside the box in the right way, with a node at each wall, which means the wave function reaches exactly zero at each boundary. And the requirement that the function have a node at each wall means that only certain wavelengths are allowed. The box must contain exactly a whole number of half wavelengths. 1 half wavelength for the lowest energy state, 2 half wavelengths for the first excited state, 3 for the second excited state, and so on. This restriction on the allowed wavelengths translates, through de Broglie's relation, into a restriction on the allowed momenta and therefore on the allowed energies. The energy of each state is proportional to the square of the state number. The ground state has energy proportional to 1 squared, the first excited state has energy proportional to 2 squared, the second excited state proportional to 3 squared. The energies are quantized. They can only take certain discrete values, not any value in a continuous range. This quantization of energy is one of the most fundamental features of quantum mechanics, and it emerges naturally from the wave nature of quantum mechanical particles. It is not imposed from outside. It is a consequence of the requirement that the wave function satisfy the boundary conditions of the problem. A wave confined in a box can only fit in the box in certain ways, and each way corresponds to a different energy. There is something else remarkable about the energy levels of the particle in a box. The lowest energy state, the ground state, does not have zero energy. It has a small but non-zero energy, the minimum energy that the particle can have while still being confined in the box. This is a completely non-classical result. In classical physics, a particle at rest in a box has zero energy. But in quantum mechanics, the act of confining a particle to a finite region introduces an irreducible uncertainty into its momentum, because knowing that the particle is inside the box tells you something about its position, which by Heisenberg's uncertainty principle means you cannot know its momentum precisely. And a particle with uncertain momentum has uncertain kinetic energy, and therefore non-zero average energy. The ground state energy of the particle in a box is a direct consequence of Heisenberg's uncertainty principle. Drift deeper now, let the mathematics soften into a general impression. The particle is in its box, its wave function a gentle sine curve, most likely to be found in the middle of the box in the ground state, unable to rest with zero energy because the universe does not permit that degree of certainty about both where it is and how fast it is moving. The interpretation of these wave functions, what they actually tell us about the location of the particle, follows directly from Born's probability interpretation. The modulus squared of the wave function at any point in space gives the probability density for finding the particle at that point. For the ground state of the particle in a box, the wave function is a single half-period sine curve, which is largest in the middle of the box and zero at the walls. The modulus squared of this, the probability density, is therefore also largest in the middle and zero at the walls. The particle is most likely to be found near the center of the box. For the first excited state, the wave function is a full sine curve. It has a node in the middle of the box as well as at the walls. The probability density, being the square of this, is zero at the walls and zero in the middle, and is peaked in 2 regions, one on either side of the center. A measurement of the particle's position in this state would find it on one side of the center or the other, but never exactly in the middle. The probability of finding it exactly at the midpoint is 0, a remarkable and completely non-classical prediction. These probability distributions can be used to calculate expectation values, the average results of measurements made on many identically prepared quantum systems. The expectation value of the position of the particle in the ground state, calculated by integrating position times probability density over the full extent of the box, comes out to exactly half the box length, the center of the box. This makes intuitive sense given the symmetry of the ground state wave function, which is symmetric about the center. The particle is equally likely to be found on the left half or the right half of the box, and so its average position is the center. The expectation value of any quantum mechanical observable, position, momentum, energy, angular momentum, is calculated in this way, by integrating the observable times the probability density over the relevant space. And the spread of the possible measurement outcomes around this expectation value is characterized by the standard deviation, which in quantum mechanics goes by the name of uncertainty. The uncertainty in position, the uncertainty in momentum, the uncertainty in energy. The relationship between these uncertainties, in particular between the uncertainty in position and the uncertainty in momentum, is governed by Heisenberg's uncertainty principle, one of the most profound and most discussed results in all of physics. The uncertainty principle states that the product of the uncertainty in position and the uncertainty in momentum can never be less than a certain minimum value, which is half of Planck's constant. The more precisely you know where a particle is, the less precisely you can know how fast it is moving, and vice versa. This is not a limitation of our measuring instruments. It is a fundamental feature of quantum reality. One of the most striking phenomena that emerges from the mathematics of quantum superposition deserves to be described carefully, because it reveals something profound about the relationship between the quantum world and the classical one. When a particle in a quantum system is not in a single energy eigenstate, but in a superposition, a mixture of two or more energy eigenstates, its behavior becomes richer and more interesting than any single eigenstate could produce. The probability density for such a superposition state is not static, but oscillates in time, shifting back and forth in space with a characteristic frequency that is determined by the difference in energy between the states that make up the superposition. Consider a particle in the infinite square well whose quantum state is a superposition of the ground state and the first excited state in equal proportions. The probability density for this state, the quantity that tells you where you are most likely to find the particle, oscillates back and forth across the box with a frequency equal to the energy difference between the two states divided by Planck's constant. At one moment, the probability is concentrated on the left side of the box. A moment later, it has shifted to the right side, and then back again, oscillating with a regularity and precision that is deeply characteristic of quantum mechanics. This oscillation frequency is not an arbitrary number. It is exactly the frequency that Bohr had used 15 years earlier in his model of the hydrogen atom to calculate the frequency of light emitted when an electron jumps from one energy level to another. Bohr's rule said that the frequency of emitted photons was proportional to the difference in energy between the initial and final states of the electron. Schrödinger's wave mechanics arrived at the same frequency from a completely different direction, not as a postulate, as Bohr had introduced it, but as a natural consequence of the mathematics of quantum superposition. This connection between the oscillation of probability density in superposition states and the emission of radiation was one of the results that gave Schrödinger confidence that his equation was not merely a mathematical device, but a genuine description of physical reality. The electron in an excited hydrogen atom could be thought of as a quantum system whose wave function was a superposition of two energy eigenstates, the excited state and the ground state. As this superposition evolved in time, the probability density oscillated, the charge distribution oscillated, and this oscillating charge distribution radiated electromagnetic energy at precisely the frequency predicted by Bohr's rule. The emission of light by atoms followed naturally from Schrödinger's equation. Let your eyelids grow heavier now. The quantum world is doing its quiet work all around you, electrons in their atoms, oscillating probability densities, photons being emitted and absorbed in the precise, quantized way that Schrödinger's equation predicts. The mathematics is running in the background of reality, always, without effort or attention, in the atoms of the air you breathe and the neurons of your brain and the stars that shine outside through the dark. The hydrogen atom was the first test of Schrödinger's equation beyond the simple models he had used to develop it, and the test was passed with extraordinary success. Schrödinger applied his equation to the three-dimensional problem of an electron orbiting a proton, the hydrogen atom, and found that the allowed energy levels predicted by his equation were exactly the energy levels that had been known empirically for decades from the spectroscopy of hydrogen. The sharp spectral lines of hydrogen, those precise wavelengths of light that hydrogen emits and absorbs, which had been measured with great accuracy but had only been explained by Bohr's somewhat ad hoc model, emerged naturally and necessarily from Schrödinger's wave equation. But Schrödinger's equation gave more than just the energy levels. It gave the spatial structure of the wave functions associated with each level, the probability distributions for the electron in each quantum state of the hydrogen atom. These wave functions, which are sometimes called atomic orbitals, have shapes that are directly relevant to chemistry. The way atoms bond to form molecules, the angles between chemical bonds, the way electrons are shared between atoms in covalent bonds. All of this chemistry is encoded in the shapes of atomic wave functions, which the Schrödinger equation determines completely. This was not a feature of Bohr's model, which had treated the electron as a particle following a definite circular orbit, and had given no information about the spatial distribution of the electron probability. Schrödinger's equation went much further, providing not just the energy levels, but the complete quantum mechanical description of each atomic state. The full wave function, with its three-dimensional structure, from which any measurable property of the atom could in principle be calculated. The verification of Schrödinger's predictions for hydrogen was rapid and comprehensive. The spectral lines were predicted correctly. The transition probabilities, the rates at which electrons jumped between energy levels and emitted photons, were predicted correctly. The intensities and polarizations of the emitted light were predicted correctly. Here was a theory that not only reproduced the known results, but provided a framework from which they could be derived, understood, and extended to more complex systems. It was for this work that Erwin Schrödinger was awarded the Nobel Prize in Physics in 1933, sharing the prize with Paul Dirac, who had independently developed an equivalent formulation of quantum mechanics. Schrödinger was 46 years old at the time of the prize, well past the age at which the conventional wisdom had suggested the great contributions in theoretical physics tend to be made. The equation that bore his name had been completed in the months after that physics colloquium in Zurich, where Peter Debye had asked how you could have a wave without a wave equation. The Schrödinger equation and the quantum mechanics built upon it did not merely explain the hydrogen atom. In the decades following Schrödinger's work, quantum mechanics was extended and applied to every domain of physical science, and its success in each domain was decisive. The structure of all atoms, not just hydrogen, was explained by quantum mechanics. The periodic table of the elements, which chemists had known for decades as an organizing principle but had never fully understood, emerged as a natural consequence of the quantum mechanical structure of atoms. Specifically, from the way electrons filled the allowed quantum states in atoms with increasing numbers of protons. The rules governing which quantum states could be filled by which electrons, governed by the Pauli exclusion principle discovered by Wolfgang Pauli in 1925, determined the chemical properties of each element and explained why the periodic table had the pattern it did. The nature of chemical bonds, the forces that hold atoms together in molecules, was explained by quantum mechanics as arising from the sharing of electron probability density between atoms. When two atoms approach each other, their electron wave functions overlap and combine, and in some cases, this combination lowers the total energy of the system, producing a stable molecule. The geometry of molecules, the angles and lengths of chemical bonds, is determined by the shapes of atomic and molecular wave functions, all of which are governed by Schrödinger's equation. The behavior of electrons in crystalline solids, the physics that determines whether a material is a conductor, a semiconductor, or an insulator, is governed by quantum mechanics. The existence of semiconductor materials, which conduct electricity under some conditions but not others, and which can be precisely engineered to control the flow of electrons, is a quantum mechanical phenomenon. The transistor, the device that makes all modern electronics possible, works because of quantum mechanical principles applied to semiconductor materials. Every integrated circuit, every microprocessor, every memory chip, every digital device is, at its most fundamental level, a quantum mechanical device. Lasers work because of quantum mechanical transitions between energy levels, electrons in atoms being stimulated to emit photons in a coherent, organized way that is possible only because of the discrete energy level structure that the Schrödinger equation predicts. Medical imaging technologies that use magnetic resonance, the MRI scanner, work by manipulating the quantum mechanical spin states of hydrogen nuclei. The global positioning system depends on atomic clocks that keep time by counting quantum mechanical oscillations in cesium atoms. All of this, every piece of modern technology that depends on the quantum nature of matter, traces its lineage back to Schrödinger's equation, to de Broglie's matter waves, to Born's probability interpretation, to the slow and careful work of a generation of physicists who were willing to follow the mathematics of quantum mechanics into a world that seemed, and still seems, deeply strange. As you sink further into the warmth of sleep, let that thought drift through you like a slow wave. The quantum world is not separate from the world you live in, it is the foundation of it. The device that played this voice to you is a quantum mechanical device. The neurons that are registering these words are quantum mechanical systems. The atoms of your body are governed, at every level, by Schrödinger's equation. You are, in a very real sense, a quantum mechanical system listening to the story of quantum mechanics. There is something in that which is either very funny or very beautiful, or perhaps both. The interpretation of quantum mechanics, what the wave function actually means, what it is describing about the physical world, remains one of the most actively debated questions in physics and philosophy. Schrödinger himself believed that his wave function described a real physical wave, a genuine oscillation of something in three-dimensional space. But this view ran into difficulties, most notably with systems involving more than one particle, where the wave function lives not in ordinary three-dimensional space, but in a much higher dimensional mathematical space whose physical interpretation is unclear. Born's probability interpretation, the view that the wave function encodes probabilities rather than definite physical facts, became the dominant view within the physics community, forming the core of what is called the Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg. But the Copenhagen interpretation has its own difficulties and ambiguities, and many physicists and philosophers have found it unsatisfying. Over the decades, other interpretations have been proposed. The many worlds interpretation, developed by Hugh Everett in 1957, proposes that the wave function never collapses, that all possible outcomes of every quantum measurement are actually realized, in different branches of a continually splitting universal wave function. In this view, there is no randomness at the fundamental level. All outcomes happen, but each observer finds herself in one particular branch and experiences only one outcome. The pilot wave theory, developed by David Bohm, proposes that there is a definite particle following a definite trajectory, guided by the wave function in a deterministic way, restoring determinism to quantum mechanics at the cost of introducing a rather unusual non-local guiding field. None of these interpretations has been shown to be wrong, because they all make the same experimental predictions as standard quantum mechanics. The debate between them is a debate about what quantum mechanics is telling us about the nature of reality, not about what it predicts. It is, in the deepest sense, a philosophical debate, though it is conducted in the language of mathematics and physics. Schrödinger himself contributed to this debate in a way that has achieved a kind of cultural immortality. In 1935, he proposed a thought experiment that has become one of the most famous in the history of physics, the thought experiment of Schrödinger's cat. Imagine a cat placed in a sealed box with a device that will release a poison if a radioactive atom decays. According to quantum mechanics, before you open the box, the atom is in a superposition of decayed and not decayed states. If the wave function describes reality, then the cat too must be in a superposition, simultaneously alive and dead, until someone opens the box and observes the result. Schrödinger intended this thought experiment as a reductio ad absurdum, a demonstration that applying quantum mechanics to macroscopic objects led to absurdity, and therefore that quantum mechanics must be incomplete or misinterpreted. But the thought experiment instead became a cultural icon, a symbol of the paradoxical nature of quantum mechanics, endlessly discussed and debated and referenced. The question it raises: at what point does the quantum superposition of possibilities collapse into a definite classical reality, is still not fully resolved. The night is deep around you now, and the story of the Schrödinger equation has reached its natural resting place. Erwin Schrödinger, who was born in Vienna in 1887 into a city buzzing with intellectual life, who received his education in the broad and careful way of his era, who survived the First World War and spent years moving between institutions without finding his great problem, who read a footnote in a paper by Einstein in October of 1925 and felt the pull of something important. That Schrödinger went to the Swiss Alps in December of 1925 and returned with an equation that opened a new chapter in the history of physics. The equation described waves, not waves of water or sound or light, but waves of probability, mathematical objects whose modulus squared at any point in space told you the probability of finding the associated particle there. Waves that satisfied boundary conditions and therefore could only exist in certain quantized forms, each form corresponding to a different energy level of the system. Waves that could be superposed, that could interfere, that could oscillate when they were combinations of different energy states, and whose oscillation frequency corresponded exactly to the frequency of light emitted when quantum systems made transitions between energy levels. The equation that Schrödinger found was not derived from more fundamental principles exactly, it was postulated, and its validity was established by comparing its predictions with experiment. And the predictions it made were correct, time after time, in domain after domain. The hydrogen spectrum, atomic structure, chemical bonding. The behavior of electrons in solids, the operation of transistors and lasers, the structure of molecules, the properties of materials, the behavior of subatomic particles. Everywhere quantum mechanics was applied, it worked. And at the center of all of it was Schrödinger's equation, that beautiful, strange differential equation with its imaginary unit and its complex wave function and its probabilistic interpretation, describing a world that was not made of definite, precisely located particles following deterministic trajectories, but of probability amplitudes evolving in time according to precise mathematical rules, collapsing into definite outcomes only when a measurement was made. And then only probabilistically. The atoms around you right now, in the air, in the walls, in your own body, are governed by this equation. Their electrons exist in quantum states described by wave functions that the Schrödinger equation determines. The chemical bonds that hold molecules together, the spectral lines that give stars their characteristic colors, the behavior of semiconductors that makes your digital devices work. All of it follows from that equation, written down in a mountain villa in Switzerland in the winter of 1925 by a physicist who was no longer young, who had wondered for years whether his best contribution was still to come, and who found it waiting for him in the question of how a wave could exist without a wave equation. The answer, it turned out, was that it could not. And in finding the equation that the matter wave required, Schrödinger gave physics the key to the quantum world, a world stranger and more wonderful than anyone had imagined, a world in which certainty gave way to probability and particles became waves, and the precise, deterministic universe of Newton turned out to be an approximation, accurate at the scales of everyday life, but revealing its quantum foundations when you looked closely enough. The story of quantum mechanics did not begin with Schrödinger, of course. It began earlier, with Planck's discovery of energy quantization in 1900, and it moved through Einstein's explanation of the photoelectric effect in 1905, and through Bohr's model of the atom in 1913. Each of these developments added a piece to a picture that was becoming, by the early 1920s, both more detailed and more puzzling. The picture showed that the classical physics of Newton and Maxwell was not wrong exactly, but incomplete, that it broke down at the atomic scale in ways that demanded new concepts and new mathematics. The Bohr model of the hydrogen atom was the most successful of these early quantum theories. It proposed that electrons in a hydrogen atom could only occupy certain discrete orbits, each with a specific energy, and that the energy of the light emitted when an electron jumped from a higher orbit to a lower one was exactly equal to the difference in energy between the two orbits. This prediction matched the observed spectral lines of hydrogen with extraordinary precision, but the Bohr model had no theoretical justification. It was a set of rules imposed by hand to make the numbers come out right, without any underlying physical principle to explain why electrons should be restricted to discrete orbits and not allowed to occupy any orbit they pleased. It was de Broglie who provided the first hint of an underlying principle. If electrons had an associated wavelength, as de Broglie proposed, then the restriction to discrete orbits followed naturally from the requirement that the electron wave fit around the orbit in a coherent way, that a whole number of wavelengths had to fit exactly into the circumference of each allowed orbit. Orbits for which this condition was not satisfied would produce a wave that interfered destructively with itself, cancelling out, and therefore could not exist as stable states. Orbits for which the condition was satisfied would produce a standing wave, a wave that reinforced itself, that persisted, that corresponded to a stable quantum state. This was a beautiful piece of physical intuition, but it was only an intuition. De Broglie had not provided a wave equation, had not shown how to calculate the wave functions in detail, had not given a prescription for applying his ideas to systems more complicated than the simple circular orbits of the Bohr model. These were the gaps that Schrödinger filled, and the filling of those gaps was what transformed the wave-particle duality from a suggestive idea into a complete and calculable theory. The development of quantum mechanics in the 1920s was one of the most intense and productive periods in the history of physics. Within a few years of Schrödinger's publication of his equation, the theory had been extended, tested, and interpreted in ways that transformed our understanding of the atomic world. Werner Heisenberg, working independently and using a very different mathematical framework based on matrices rather than waves, had developed an equivalent formulation of quantum mechanics slightly before Schrödinger, and the equivalence of the two approaches was demonstrated by Schrödinger himself in 1926. Paul Dirac, the brilliant and famously laconic English physicist, unified and extended both formulations into a single mathematical framework of extraordinary generality, and then took the further step of making quantum mechanics consistent with special relativity, producing the Dirac equation in 1928. The Dirac equation predicted not only the correct quantum mechanical behavior of the electron, but also the existence of antimatter. It implied that for every particle, there was an antiparticle with the same mass, but opposite charge. The positron, the antiparticle of the electron, was discovered experimentally in 1932, confirming one of the most striking predictions that had ever been made on purely theoretical grounds. All of this, Heisenberg's matrices, Schrödinger's waves, Dirac's relativistic extension, the statistical interpretation of Born, the uncertainty principle, the Pauli exclusion principle, came together in the late 1920s into a coherent framework that physicists called quantum mechanics. It was a framework of remarkable power and generality, applicable to any physical system for which the relevant forces and interactions could be specified, and its predictions, wherever they could be tested, were confirmed. There is a particular quality to the strangeness of quantum mechanics that deserves to be explored a little further, because it is not the ordinary strangeness of things that are unfamiliar or counterintuitive simply because we have not encountered them before. Quantum strangeness is deeper than that. It is the strangeness of a fundamental theory that seems to resist being made sense of in terms of the ordinary concepts we use to describe the everyday world. Consider what the wave function actually is. It is a mathematical function defined at every point in space, complex-valued, evolving in time according to Schrödinger's equation. But what is it a function of? What does it describe? Born says it describes probabilities, the probability of finding the particle at various locations if a measurement is made. But this raises an immediate question. What is a measurement? What happens when a measurement is made that transforms the smooth, continuous evolution of the wave function into a definite outcome? In ordinary quantum mechanics, as it is taught and practiced, the wave function evolves according to Schrödinger's equation in between measurements. But when a measurement is made, the wave function does not evolve in this smooth way. It jumps discontinuously to a new state that is consistent with the measurement outcome. This jump is called the collapse of the wave function, and it is one of the most problematic aspects of quantum mechanics. The collapse is not described by the Schrödinger equation. It is an additional postulate, something added to the theory to account for what happens at the moment of measurement, and it raises a host of questions. What counts as a measurement? Does a measurement require a conscious observer, or does any physical interaction suffice? At what scale does the quantum behavior of superposition give way to the classical behavior of definite outcomes? Is the collapse of the wave function a real physical process, or is it just a change in our knowledge? These questions, which go under the collective heading of the measurement problem, are not resolved by quantum mechanics as it stands. They are, in a sense, the gap between the beautiful mathematics of the Schrödinger equation and the actual experimental world in which physicists make measurements and record outcomes. The mathematics is impeccable. The predictions are correct. But the connection between the mathematics and the physical world, the interpretation, remains a matter of ongoing debate. This should not be taken as a sign that quantum mechanics is somehow deficient or incomplete in a way that will be fixed by a better theory. It may be, and many physicists believe it is, that the measurement problem reflects something genuinely puzzling about the nature of reality, that the universe at the quantum level really is described by a wave function that does not correspond to any single definite classical state. and that the apparent definiteness of classical outcomes emerges from quantum mechanics in a way that we do not yet fully understand. Let your mind rest easy at that edge of understanding as your breathing slows and the night deepens. The universe does not require us to understand it completely in order to run. It has been running beautifully for 14 billion years without our comprehension, and it will continue to do so. The questions that remain open are not failures of human intelligence, but invitations, open doors into territory that still waits to be explored. The wave nature of quantum particles was not merely a theoretical proposal after de Broglie and Schrödinger. It was confirmed decisively by experiment, and the experimental confirmation had a beauty of its own. In 1927, the same year that Heisenberg published his uncertainty principle, Clinton Davison and Lester Germer at Bell Laboratories in New York performed an experiment that provided direct evidence for the wave nature of electrons. They directed a beam of electrons at a crystal of nickel and observed the pattern of electrons reflected from the crystal surface. Crystals have a regular periodic structure. The atoms in a crystal are arranged in a precise lattice, with regular spacing between them. When waves encounter a periodic structure, they diffract. They produce interference patterns, with some angles showing constructive interference and others showing destructive interference, producing a characteristic pattern of peaks and troughs. Davison and Germer observed exactly such a diffraction pattern in their electron beam. The electrons were not scattered randomly in all directions, as they would be if they were purely classical particles bouncing off the individual atoms. They were scattered in a pattern of discrete peaks, at angles that corresponded exactly to the wavelengths predicted by de Broglie's relation for electrons moving at the measured velocities. The electrons were diffracting, they were interfering, they were, in every observable respect, behaving like waves. This was one of the most important experimental results of the 20th century. It confirmed that de Broglie's hypothesis was not merely a mathematical analogy, but a physical reality. Electrons were waves, and they diffracted and interfered exactly as waves should. The Nobel Prize was awarded to Davison and Germer's collaborator George Thomson in 1937 for the experimental confirmation of electron diffraction, a prize that has a certain irony to it, since Thomson's father, J.J. Thomson, had received the Nobel Prize in 1906 for demonstrating that electrons were particles. Father and son each received a Nobel Prize for demonstrating complementary aspects of the dual nature of the electron. The wave nature of particles is not restricted to electrons. Protons and neutrons, atoms and molecules have all been shown to diffract in exactly the way that de Broglie's relation predicts. The record for the largest object shown to exhibit quantum wave behavior is held, at the time of writing, by molecules containing hundreds of atoms, objects large enough to be visible under a microscope, yet still capable of producing quantum interference patterns when they pass through appropriately designed slits. The quantum world is not a world of subatomic particles only. It is the world, period. The quantum nature of matter is present at every scale, though it manifests in ways that are increasingly difficult to observe as the objects in question become larger. One of the most beautiful applications of the Schrödinger equation, beautiful both mathematically and physically, is to the phenomenon of quantum tunneling. In classical physics, if a particle does not have enough energy to surmount a barrier, it cannot get to the other side. A ball rolling toward a hill that is taller than the ball's kinetic energy can reach will simply roll back down. The barrier is impenetrable. Classical physics is absolute on this point. But in quantum mechanics, the wave function of a particle does not simply drop to zero at the edge of a barrier. It penetrates into the barrier, decaying exponentially as it goes, and if the barrier is not too thick, there is a non-zero probability of finding the particle on the other side. The particle has, in effect, tunneled through the barrier, passed through a region that classical physics would forbid, not by gaining extra energy, but by virtue of its wave nature. The wave function extends into the classically forbidden region and has a non-zero amplitude on the far side. This quantum tunneling is not a theoretical curiosity. It is a physical reality with profound consequences. The nuclear fusion reactions in the cores of stars, the reactions that generate the energy that makes stars shine, that warms planets, that makes life possible, occur because protons can tunnel through the electrostatic barrier that would otherwise prevent them from getting close enough to interact by the strong nuclear force. Without quantum tunneling, the sun would not shine. Stars would not exist. The universe would be a very different and much darker place. Quantum tunneling is also the physical mechanism behind the scanning tunneling microscope, invented in 1981 by Gerd Binnig and Heinrich Rohrer at IBM, who received the Nobel Prize in Physics in 1986. The scanning tunneling microscope works by bringing an extremely sharp metallic tip to within a few atomic diameters of a surface and measuring the tiny electric current that flows between the tip and the surface through quantum tunneling. Because the tunneling current is exponentially sensitive to the distance between the tip and the surface, small variations in the surface topography produce large variations in the current, allowing the microscope to image individual atoms on a surface. The scanning tunneling microscope gave humanity its first direct images of atoms, individual atoms, visible and distinguishable, their positions mapped by the quantum mechanical tunneling of electrons. Quantum tunneling is also at work in the transistors at the heart of modern electronics, where it sets fundamental limits on how small transistors can be made before tunneling currents cause them to malfunction. As transistors have shrunk to the nanometer scale in modern integrated circuits, quantum tunneling has become an increasingly important constraint on their design. Managing quantum tunneling is one of the central challenges of modern semiconductor engineering. All of this, the shining of stars, the imaging of atoms, the limits of modern electronics, follows from the Schrödinger equation and the wave nature of quantum particles. The equation that Schrödinger wrote in a mountain villa in the winter of 1925 continues to shape the world in ways large and small, visible and invisible, every day. The story of quantum mechanics is, in part, a story about the limits of human intuition. Our intuitions about the physical world were formed in an environment where quantum effects are negligible, where objects are large enough and slow enough and warm enough that the classical approximation is essentially exact. We evolved to navigate a world of medium-sized objects, and our cognitive architecture reflects that evolutionary history. We find it natural to think of things as having definite positions and definite velocities. We find it natural to think of the future as determined by the past. We find it natural to think of a measurement as simply revealing a pre-existing fact about the world. Quantum mechanics challenges all of these intuitions. Particles do not have definite positions and velocities simultaneously. The future is not fully determined by the past. Only the probabilities of different futures are determined, and a measurement does not simply reveal a pre-existing fact, it plays a role in creating the outcome. These are not easy things to accept, and the history of quantum mechanics is full of the discomfort of physicists who understood the theory perfectly well, but found it deeply unsatisfying as an account of physical reality. Einstein, as we have noted, spent the last decades of his life trying to demonstrate that quantum mechanics was incomplete, that there must be hidden variables underlying the quantum probabilities that would restore determinism at a deeper level. His efforts produced some of the most penetrating critiques of quantum mechanics ever written, and they eventually led, through the work of John Bell in the 1960s, to experimental tests that showed that no local hidden variable theory could reproduce all the predictions of quantum mechanics. The universe really was, in the sense that Bell's theorem and subsequent experiments demonstrated, irreducibly non-local and irreducibly probabilistic, at the quantum level. This is where physics stands today with respect to the interpretation of quantum mechanics. The mathematics is clear and agreed upon. The predictions are precise and confirmed. But what the mathematics is describing, what the wave function really is, what happens at the moment of measurement, how the classical world of definite outcomes emerges from the quantum world of superposed possibilities, remains a matter of active investigation and genuine philosophical disagreement. It is a remarkable situation, and it speaks to the depth of what quantum mechanics has revealed. The theory is nearly a century old, and its mathematical structure is thoroughly understood. Yet the question of what it means, what it tells us about the nature of reality, is still open. That openness is not a failure. It is a measure of how far quantum mechanics has taken us beyond the limits of ordinary experience, into territory where our concepts strain and our intuitions fail, and the mathematics itself becomes the most reliable guide we have. As you drift towards sleep, let that thought be the last one, not as something to worry about, but as something to find peace in. The universe is deeper than we can fully comprehend. That depth is not a problem. It is the invitation that has driven physics forward for 3 centuries, from Newton to Maxwell, to Planck to Einstein to Schrödinger to Dirac, and all the generations that have followed. Each generation has pushed a little further into the unknown, and each step forward has revealed a larger and more surprising universe than the one they started from. The next generation will push further still. And the Schrödinger equation will still be there, governing the atoms and the electrons and the photons, as it has governed them since it was written, steady and exact, and quietly indifferent to whether anyone is paying attention. The philosophical implications of quantum mechanics reach beyond physics into questions that have occupied human beings since the beginning of recorded thought. Questions about the nature of knowledge, the relationship between the observer and the observed, the meaning of causality, and the ultimate structure of reality. For most of the history of science, the assumption underlying all inquiry was that the natural world existed independently of any observer, that its properties were definite and objective, and that the role of science was simply to measure and record those properties as accurately as possible. The measuring instrument was an incidental detail, something to be refined and calibrated but fundamentally transparent, a window onto a reality that would be exactly the same whether anyone was looking or not. Quantum mechanics challenged this assumption in a way from which there is no simple retreat. The wave function of a quantum system encodes probabilities for various measurement outcomes, and those probabilities change depending on what is measured and how. The quantum state of a system is not simply a description of pre-existing definite properties. It is something that involves, in an irreducible way, the relationship between the system and the measuring apparatus. The properties of a quantum system are not all simultaneously definite, and which properties are definite depends on what you are measuring. This does not mean that quantum mechanics is subjective, that reality is merely a construction of the observer's mind. The predictions of quantum mechanics are objective and reproducible. The same quantum state, measured in the same way by different observers, yields the same statistical distribution of outcomes. But it does mean that the classical picture of an objective world of definite properties existing entirely independently of any observation is, at the quantum level, untenable. Niels Bohr, who was perhaps the deepest thinker among the founding generation of quantum mechanics, spent decades exploring the implications of this situation. He developed the concept of complementarity, the idea that quantum systems have multiple aspects that are mutually exclusive, that cannot be observed simultaneously, but that are all necessary for a complete description. The wave aspect and the particle aspect of quantum systems are complementary in this sense. You can set up an experiment to observe one or the other, but not both at the same time. The position and the momentum of a particle are complementary. Precise knowledge of one excludes precise knowledge of the other. Complementarity was Bohr's attempt to make philosophical sense of quantum mechanics without reducing it to classical terms. It was not universally accepted. Einstein, in particular, resisted it, but it has been enormously influential and remains one of the most thoughtful responses to the conceptual challenges that quantum mechanics poses. The uncertainty principle that Heisenberg discovered in 1927 is one of the most precise expressions of quantum complementarity. It states that the product of the uncertainty in a particle's position and the uncertainty in its momentum cannot be less than a certain minimum value, proportional to Planck's constant. This is not a statement about the limitations of our measuring instruments. It is a statement about the nature of quantum states themselves. A quantum state that is perfectly localized in position, one for which the particle's location is precisely defined, is necessarily a superposition of momentum states spanning the full range from -infinity to +infinity, and therefore has completely undefined momentum. Conversely, a state of precisely defined momentum is a wave spread out over all of space, with completely undefined position. Position and momentum are not independently definite properties that we simply fail to measure simultaneously. They are aspects of the quantum state that are genuinely incompatible. A state that is definite in one cannot be definite in the other. Schrödinger lived a long and intellectually productive life beyond the discovery of his equation. He continued to think and write about the foundations of quantum mechanics and about the broader implications of physics for our understanding of reality. In 1944, he published a small but influential book called What is Life?, in which he applied the concepts of quantum mechanics and thermodynamics to the problem of biological heredity, arguing that the genetic material must be an aperiodic solid, a molecule with an irregular but stable structure capable of encoding information. This book was read by Francis Crick and James Watson, who credited it as one of the inspirations that led them to work on the structure of DNA. When Watson and Crick published their famous double helix paper in 1953, Schrödinger's prediction had been confirmed. DNA is precisely the kind of aperiodic solid he had described, its irregular sequence of base pairs encoding the genetic information of living things. It is a remarkable arc, from the wave function of the electron to the structure of the molecule of life, and it illustrates the extraordinary reach of the conceptual framework that quantum mechanics provides. The same ideas that explain the energy levels of hydrogen atoms and the behavior of electrons in semiconductors also illuminate the nature of heredity and the molecular basis of life. Schrödinger received the Nobel Prize in Physics in 1933. He spent the Nazi period in exile, first in Oxford, then in Graz, eventually making his way to Dublin, where the Irish government had established the Dublin Institute for Advanced Studies specifically to attract distinguished scholars fleeing fascism. He spent 17 years in Dublin, working on a unified field theory, thinking about the philosophy of science, writing about the relationship between physics and consciousness, and enjoying the intellectual and social life of the city. He returned to Vienna in 1956, to the city of his birth, to take up a professorship at the University of Vienna. He was 68 years old, and Vienna had changed enormously from the city of coffee houses and intellectual ferment where he had grown up. But it was home, and he spent the last years of his life there, writing, thinking, and receiving visitors who came to pay respects to one of the great physicists of the 20th century. He died in Vienna in January of 1961 at the age of 73. The equation that bore his name was by then already woven into the fabric of modern civilization, running in the mathematics of every atom, expressed in the design of every transistor, manifested in the light of every laser. It will continue to run, unchanged and exact, for as long as the universe contains atoms and waves and the particular kind of physical reality that quantum mechanics describes, which is to say, forever. The stars outside are very old and very far away. The light reaching you from the nearest ones left its source years ago. The light from the most distant galaxies has been traveling for billions of years through an expanding universe, carrying with it information about the quantum mechanical processes, the nuclear reactions in stellar cores, the atomic transitions in stellar atmospheres that produced it. Every wavelength of that starlight, every color in the spectra of distant stars is a quantum mechanical fingerprint. The Schrödinger equation is running in the cores of stars a billion light years away, as surely as it is running in the atoms of your body. There is something in that which is both enormous and intimate at the same time. The same mathematics that governs the glow of a hydrogen gas discharge tube in a physics laboratory also governs the light of a quasar at the edge of the observable universe. The same equation that explains the colors of fireworks, the atomic transitions of strontium and barium and copper, each producing its characteristic wavelength of light when electrons fall from excited states to lower ones, also explains the absorption lines in the spectra of stars, the dark bands that tell astronomers what elements are present in stellar atmospheres billions of light years from here. The universe is a quantum mechanical system, and it is running its equations with absolute faithfulness across every scale of space and time that we can observe. Let the enormity of that settle into the background of your awareness as sleep approaches, not as something demanding to be grasped, but as a background hum, the universe doing what it does, with the patient regularity that has characterized it since the first atoms formed in the cooling aftermath of the Big Bang, following the laws that govern the behavior of matter and energy at every scale. The Schrödinger equation is one of those laws. A partial differential equation with an imaginary unit and a complex wave function and a probabilistic interpretation. Beautiful in its form, extraordinary in its reach, still not completely understood in its deepest implications. A door opened in a winter villa in the Swiss Alps, leading into a quantum world that is strange and wonderful and precisely mathematical and still, even now, full of questions that no one has yet answered. That is where you are tonight. In a universe governed by quantum laws, breathing quantum mechanical air, lying on a bed of quantum mechanical atoms, your quantum mechanical neurons processing the quantum mechanical words of this story and preparing to release their grip on waking consciousness and sink into the particular kind of unknowing that we call sleep. The wave function of your awareness is collapsing, moment by moment, into the definite state of rest. Let it. The legacy of the Schrödinger equation extends into corners of science and technology that Schrödinger himself could not have imagined. When he wrote his equation in 1926, the transistor was more than 20 years in the future. The laser did not exist. The structure of DNA was unknown. The concept of a digital computer, while being developed in rough theoretical outline by Alan Turing, was still far from practical realization. The idea that human beings would one day carry in their pockets devices containing billions of transistors, connected by invisible electromagnetic waves to a global network of information, would have seemed like the wildest science fiction. Yet all of it rests, ultimately, on the foundation that Schrödinger laid. The transistor works because of the quantum mechanical behavior of electrons in semiconductor crystals, the way electrons fill energy bands, the way certain materials can be made to conduct or insulate depending on the presence of impurities, the way the interface between different semiconductor materials creates quantum mechanical potential wells and barriers that electrons can be manipulated to cross or not cross. None of this can be understood without quantum mechanics. None of it could have been engineered without the theoretical framework that the Schrödinger equation provides. The laser works because of stimulated emission, the process by which a photon passing through a collection of excited atoms can stimulate those atoms to emit additional photons in the same direction and with the same phase, producing a coherent beam of light of extraordinary intensity and monochromaticity. The theory of stimulated emission was worked out by Einstein in 1917, but understanding how to use it to build a practical device required the full machinery of quantum mechanics, including the detailed understanding of atomic energy levels that the Schrödinger equation provides. The laser is a quantum mechanical device in the most literal sense. It works by directly exploiting the discrete energy level structure of atoms that Schrödinger's equation predicts. Medical imaging technologies based on nuclear magnetic resonance work by manipulating the quantum mechanical spin states of atomic nuclei, primarily hydrogen nuclei, in the presence of strong magnetic fields and radio frequency pulses. The quantum mechanical behavior of nuclear spins is described by equations that are mathematically analogous to the Schrödinger equation, and the signal that an MRI machine detects is the quantum mechanical precession of nuclear spins returning to equilibrium after being perturbed. MRI images of the human body are, in a very direct sense, quantum mechanical measurements of the distribution of hydrogen atoms in different chemical environments within tissues. Quantum cryptography, the use of quantum mechanical principles to transmit information in a way that is provably secure against eavesdropping, is a technology currently transitioning from the laboratory to practical deployment. It works because of the quantum mechanical principle that measuring a quantum state generally disturbs it. An eavesdropper attempting to intercept a quantum communication cannot do so without leaving a detectable trace. The security of quantum cryptography is not a matter of computational difficulty, like conventional cryptographic security, but of the laws of physics themselves. Quantum computing, the use of quantum mechanical superposition and entanglement to perform certain computations exponentially faster than any classical computer, is being actively developed by research groups and technology companies around the world. Quantum computers exploit the fact that a quantum system in a superposition of states can, in a sense, explore all possibilities simultaneously, and careful design of quantum algorithms can harness this parallelism to solve certain problems that would take classical computers longer than the age of the universe. All of these technologies, mature and nascent alike, trace their lineage to the equation that Schrödinger wrote in the winter of 1925. That equation governs the behavior of the quantum systems at the heart of each technology, and without the theoretical framework that the equation provides, none of them could have been understood, designed, or built. The relationship between fundamental physics and technology is sometimes described as distant. The idea that pure physics is pursued for its own sake, out of curiosity, with no immediate practical application in mind, and that the applications emerge later, often in ways that the original researchers could not have predicted. The story of quantum mechanics is perhaps the most striking example of this pattern in the entire history of science. Schrödinger was not trying to invent the transistor. He was trying to find the wave equation for matter waves, driven by intellectual curiosity and the challenge posed by a colleague at a physics colloquium. That he succeeded, and that his success would eventually give rise to the entire digital world, is a testament to the extraordinary power of pure theoretical inquiry to shape the practical future. Let that thought rest gently as your eyes grow heavy and the world grows soft. The quantum world is not remote. It is here in everything, running its precise and beautiful mathematics without pause, without error, without any need for human attention or understanding. And yet human attention and understanding, the particular kind of focused, rigorous, creative thinking that Schrödinger and his contemporaries brought to the problem of matter waves, unlocked that hidden world and made its resources available to civilization in ways that continue to unfold. The equation is a gift, not a gift that was given to us. Gifts imply a giver, and the equation was always there, running in the atoms of everything, waiting to be discovered. It is a gift in the sense that understanding it opened possibilities that were previously invisible. It is a gift in the sense that the knowledge, once gained, cannot be ungained, and the world it made possible cannot be unmade. You are living in that world tonight. It is the world the Schrödinger Equation built. And it is, for all its strangeness and all its unresolved questions, a very good world to live in, full of light and connection and the persistent, irrepressible human desire to understand. One final thought before sleep arrives completely. Schrödinger, toward the end of his life, wrote and spoke about the relationship between science and human experience with a depth and a sensitivity that went beyond the technical concerns of physics. He was interested in consciousness, in the relationship between the physical world described by science and the inner world of experience, perception, and awareness. He believed that this relationship was one of the deepest unsolved problems in all of human knowledge, and he did not think that physics, even quantum physics, had yet provided a satisfying answer. The question of consciousness, of why there is subjective experience at all, of why the processing of information in a physical system should be accompanied by the felt quality of awareness, is as open today as it was in Schrödinger's time. Some physicists have speculated that quantum mechanics might play a role in consciousness, that the superposition and entanglement of quantum states might be relevant to the way the brain processes information. These speculations remain highly controversial and are not accepted by most neuroscientists or physicists. But the question itself, the hard problem of consciousness, as the philosopher David Chalmers named it, remains genuinely open. What is clear is that the universe contains, as one of its features, the phenomenon of awareness. That physical matter, organized in certain ways, the way it is organized in your brain right now, gives rise to experience, to the felt sense of warmth and comfort and drowsiness that you are experiencing as you read these words, to the soft blur of awareness as sleep approaches, to the particular quality of this moment, late in the night, as the story of quantum mechanics settles into the background of consciousness and the foreground begins to soften and dissolve. You are a quantum mechanical system becoming quiet. The quantum mechanical activity of your neurons is shifting into the patterns of sleep, slower, more synchronized, governed by the same Schrödinger equation that governs every electron in every atom, in every molecule, in every cell in your body. The boundary between the story and the sleep is becoming indistinct. That is as it should be. Let it happen. The universe will keep its equations running while you rest. It always does. It always has. As we come to the end of our journey tonight, the story can begin to settle around you. We have traveled from a Vienna apartment in 1887 to a physics colloquium in Zurich, from the matter waves of de Broglie to the wave equation of Schrödinger, from the probability interpretation of Max Born to the particle in a box and its discrete energy levels and its oscillating superposition states. We have touched the hydrogen atom and the periodic table and the transistor and the laser, and we have stood at the edge of the great unresolved questions about what quantum mechanics means about the nature of reality. It is a long journey to have made in a single night, and you do not need to hold any of it tightly. You can let the details soften into impressions now. The image of a wave function, gently sinusoidal, most probable at the center. The thought of an equation that governs the atoms of everything. The memory of a physicist who found his great problem late and solved it completely. There is no need to remember the mathematics. The mathematics will keep. It has been keeping for nearly a century, running quietly in the background of reality, governing every atom and every photon in the universe, whether or not anyone is thinking about it. It will still be there in the morning, unchanged and exact. Let your breathing slow. Let your body settle into wherever it is. The universe is doing its quantum accounting all around you, electrons in their orbitals, photons traveling at the speed of light, probability densities evolving according to Schrödinger's beautiful equation. And none of it requires your attention tonight. The wave function of the universe is evolving just as it always has. Steady, patient, precise, and kind. Sleep well, good night. Still drifting. Let the rain take over from here. Close your eyes and let it wash everything away.